Hi, I'm Scott Welch, and I'm going to be the group reporter for the bomb calorimeter experiment. So a brief overview, we're going to go over the experiment objective, what exactly a calorie is, as well as the experimental procedure, data reduction, and the thermal capacitance and heat of combustion calculations. So the overall objective was to determine the thermal capacitance of the oxygen bomb calorimeter, as well as to determine the gross heat of combustion for an unknown fuel source. So what is a calorie? A calorie is the amount of energy required to raise 1 gram of water through 1 degree of Celsius. Also comparing it to joules, it's approximately 4.187 joules. This is commonly mistaken for what we see on the back of a nutritional, facts and information that they give on the back of just about any package. And I looked up some facts about that, and it said that a calorie for the nutritional facts is about the energy to raise 1 kilogram of the substance through 1 degree Celsius. Getting into the experimental parameters. The benzoic acid, with the heat of combustion was given. It was given as 6,318 calories per gram. And then for the unknown fuel source, that's part of this experiment, is to determine that heat of combustion. We also use this fuse wire, and it linearized the amount of calories to the length of wire that you use. It's about 2.3 calories per centimeter, and we used 10 centimeters for this experiment. And then the bomb capsule was filled with about 2 kilograms of water in the bomb. We used the first law of thermodynamics to determine the thermal heat capacitance of the bomb calorimeter. Mass times the specific heat is equal to the thermal heat combustion divided by the change in temperature. The thermal capacitance of the system is measured in calories per degree Celsius. Heat was calculated in calories, and our temperature was calculated in degrees of Celsius. So how do we determine this change in temperature? I plotted the change in time versus change in temperature, and then took a mean value of the max and min of values that I got. So for the benzoic acid, I got a differential temperature of about 2.3 degrees Celsius. And then when we weighed our benzoic acid tablet, it came out to 1.01 grams. We measured out 23 calories of wire that was loaded into the bomb. After the process, after the explosion, there was about 5 calories remained, so we had 18 calories consumed. Plugging all those known values into our equation, I got a thermal capacitance of about 2,700 calories per degree Celsius for the benzoic acid. For the unknown fuel source, it did the same process. Our differential temperature was about 1.4, so slightly less than the benzoic acid. And when we weighed it, it came out to 1.04 grams. And there was 6.5 calories remained from the wire that was left over, giving us 16.5 calories consumed. And our thermal capacitance came out to about 4,700 calories per degree Celsius. For the heat of combustion, unknown fuel had, as I said before, 1.04 grams combusted. Plugging that all into our equation and using our thermal capacitance number, we got a heat of combustion of about 3,800 calories. So now I'm going to compare that to what you would see using the nutritional facts. Given on the back of the package, it was about 200 calories per 28 grams. So that gave me 7,000 calories per gram. That's a little less than double what we were getting using thermodynamics and those types of equations rather than the nutritional facts. So where did the error occur? Where do we see it? It could be in the spatial defects of the temperature readings, the differing method of nutritional generation, and then imprecise weighing of the fuel samples. Also, one thing I didn't mention was also the taking the mean temperature difference. There could be some error there. Does anybody have any questions?